Okay, so strengths of oxidizing and reducing agents. Now the rule is that as say the strongest oxidizing agents in the table of standard electrode potentials are the oxidized species corresponding to the half reactions with the largest, most positive E values. So if you have your table, I'm not going to draw it out. As you move down in this direction, you get stronger oxidizing agents. And then for reducing agents, make sure it's on there, the strongest reducing agents in a table of standard electrode potentials are the reduced species corresponding to half reactions with the smallest or most negative E values. So stronger reducing agents. So if you're given something like this, put this following species in order of increasing oxidizing agent strength. You'd have to go, if you have the table, you look and you see lithium is at the top. I'm just going to put them in order, the order they appear in the table first. Lithium, and then cadmium, and then silver. So they want the increasing oxidizing strength. They said it increases as we move down. So we would have, so it would be put in increasing order, so it would be lithium is not as strong as cadmium, which is not as strong as silver. So that's fine, but let's try to understand why that works. So if you're just given a list of them, you just look at your table. You'd be given, in my class, you'd be given the table and you'd just put them in order according to this scheme. Oxidizing agents increase as we move down, reducing agents as we go up. First thing is, these have to be oxidizing agents, they have to be able to accept electrons. So if I had here lithium, with it not lithium plus, then that wouldn't be an oxidizing agent at all. But normally you don't do that. You don't mess around with that. You just assume that everything that here is an oxidizing agent. So let's look at lithium, and let's have it oxidize something. I'm just going to pick, what did I pick? I did these out. Let's sodium. So let's have this reaction. And this is aqueous, solid, solid, aqueous. So what's happened here is the lithium has stolen an electron away, creating sodium plus and reducing itself, so it is definitely an oxidizer. Now let's look at the, I'm not going to put all the phases in here. This is minus 3.04. And then the sodium is oxidized by the oxidizing agent, so we flip its number around and it becomes plus 2.71. 2.71, yeah. And then this is minus 0.33 volts. So this E value is less than 0, so this is a non-spontaneous reaction. So lithium plus here doesn't even want to do this reaction. If it does it, it does very, a very small amount. Now let's look at silver. We'll go in the order that they have them here. We'll have it do the same thing, and again, just to speed things up, I'll leave off the phases, but you should have them in there. Sodium has the same sodium to sodium metal, sodium ion, so it's still plus 2.71, and silver is reduced, so it's 0.80. So this becomes 3.5. Now this is a very large positive number, so silver is a great oxidizing agent. And it reduces itself very easily. And then we have cadmium. Now we have to take into account the charge. So this would be 2 sodium, but remember that potential doesn't change just because we have different ratios of these species. So again, sodium is, if I could certainly write out the half reactions like I did here, but I'm not going to. For sodium, it's still 2 plus 2.71, and cadmium is minus 0.4. Make sure that's right. So this is 2.31. So if we look at these numbers, we go by the larger the positive value, the greater the reducing agent. So this one is the best, So that's the silver, this one's second, cadmium, and then the last one is lithium. That's what we found with the numbers. That's what we determined here. So just you can see what makes it a stronger oxidizing agent, what makes silver a stronger oxidizing agent than lithium or cadmium is that it has a higher E cell value, which relates back to the spontaneity. The higher the positive value, the more spontaneous it is, the more it shifts to the right. Now this negative value, this is non-spontaneous, but it still goes to some degree to the right, very, very slightly. Though that's one of the, like any equilibrium, there's always that, there's the predominating reaction to the left or right, but there's always that, the other reaction in the reverse. Okay, now let's go look at reducing agents. So putting my numbers on there. So we have aluminum, lead, and chromium. And we learned that the reducing agent, let me get the stronger the reducing agent, the further up it's going to be in the table. So we look in the table, we just put them in order. We have aluminum is found at the top, lead is below that, and chromium is in between. So what we should find is that the strength of aluminum should be the strongest reducing agent. So let's find, and if that's all you want to know about it, that's as far as you want to go with it and you understand it and you're done, but I want to just show what happens. So let's have aluminum, lead, and chromium reduce the same thing, zinc. So we'll do this out a little quicker than last time, but we find that aluminum, it's, well, let me do it once here. Aluminum going to aluminum plus 3 electrons is the reverse, that's the oxidation of the oxidation form, and they have the reducing form, or the reduction form in the table. So this is plus 1.66. We have to take the negative value of that, the original of the reduction value, which was negative 1.66. So we change the sign. And then the zinc, it's plus 2 electrons goes to zinc. And remember, even though this is a 2 and a 3, we don't touch the value of the reduction potentials, or the, I guess in this case it's the oxidation potential. This is 0.9 volts. So this reaction does go, and it's not as high as some, but it's certainly not bad. So it is definitely a spontaneous reaction. The lead, we get minus 0.76 for the zinc, and then for the lead it's 0.13. So this is minus 0.63. So this lead as a reducing agent is not very good because it doesn't, it's not spontaneous. So far aluminum is beating the lead. And then we have the 2 chromium. And chromium is plus 3, yeah, okay, so. And what we end up with is minus 7.76 for the zinc half reaction, and then we have plus 0.74. So this comes up to be minus 0.02. So it's almost spontaneous. So that we should expect that there'd be some sort of equilibrium where we'd see noticeable amounts on both sides, but it certainly is not spontaneous like the aluminum. So we'd say that lead would be the worst, because it's a very non-spontaneous reaction, and then chromium, and then aluminum, and that's what we said here. So you can look at the table, and that's fine, but I just wanted to show you why it is that happens. And we could have used anything we wanted here. This would have worked for any of the metals or hydrogen that's in the table. We would have still come up with the same sequence. Maybe they'd all have been positive, but this would be the most positive. Maybe they were all negative, but this one would be the least negative. And they'd still all follow in the same order.